Yeah, I've titled this talk a whirlwind tour of automatic speech recognition because the material being covered here is really actually enough for an entire semester's course if we wanted to go into full detail. And obviously we don't have a full semester here. You have 2 weeks, and you're not here to just hear me talk for that whole 2 weeks. So what I want to talk about is first just a brief history of speech recognition. Sanjeev touched on some of what I had to say, but this will be a slightly different take. Then I want to cover the probabilistic approach to automatic speech recognition, which again you've seen some of the pieces of already because this is the standard framework that we do speech recognition in nowadays. Then I'm going to go through the components of a standard speech recognition system, the acoustic feature extraction, acoustic modeling, language modeling, and the search process, and then just try to give you, again, some perspective on where the technology stands, what works, what doesn't. Again, some of this overlaps pretty much with Sanjeev's talk, but you're getting it from a different perspective, and because this is new material for some of you, repetition is always a good thing. So, brief history. Probably the first commercially successful speech recognition system was a toy called Radio Rex, which was sold in the 1920s. What you had was a small celluloid dog that sat inside of a doghouse. And the way the toy worked was that there was a iron base that the dog sat on, held in place by an electromagnet against the force of a spring. Now, this electromagnet was energized through a metal bar that sat on top of sort of a bridge. And the bridge was designed to resonate at about 500 hertz. So if you said Radio Rex to this thing loud enough, you had a fairly strong 500 hertz component in the in Rex, or the R in radio and Rex. The bridge would vibrate. You're at a resonant frequency, it vibrates enough, it interrupts the current going to the electromagnet, which switches off, the dog pops out of the house. It was enough to entertain people, and it sold. So moving on from the 1920s, there's actually been a lot of interest in doing computer or electronic speech recognition. And so you look back and you see people trying to do digit recognizers using analog circuitry, or trying to do very simple pattern matching with computers as soon as digital signal processing started to take off. And the one thing that characterized most of these approaches was that they were very, very strongly limited by the available computing power. So they had to use very ad hoc methods, small vocabularies, things like digits, yes or no, isolated vowels, a very small number of speakers, fairly simple signal processing methods that tried to incorporate some sense of speech knowledge, but also maybe some statistical modeling that you tried to learn parameters from data. So the field progressed in this manner for quite a while. And then there was something of a turning point in 1969 when John Pierce, who was the director of communications research at Bell Labs, which was actually home to a significant amount of speech recognition research, wrote this letter to the editor of the Journal of the Acoustical Society of America titled Whither Speech Recognition. And he actually had some criticisms of speech recognition that are still valid today and still things that we need to think about. So his first point was that people understand speech. They don't just recognize words, but they hear these words, they get a message, and they take some sort of an action based upon it. And his perspective was that at some level, speech recognition is AI complete. To really get it right, you have to have all of the knowledge of a human to do it. And because of this, perhaps the enterprise of simply recognizing words from the audio was doomed to failure. The second point that he made was that there was far too much emphasis put on tuning system parameters to get the best possible performance. This is also a valid point that we need to think about today. If you go to a speech recognition laboratory, people are going to spend a lot of time trying to optimize their parameters. And this can actually be a huge time sink and distract you from actually getting real research and real thinking done. The flip side of these, however, is that in most of the cases where we have done work on trying to do something more along the lines of speech understanding, we found that simply looking at the number of words that we get right, the rate at which we make errors, it's actually a pretty good proxy for how an end-to-end system is going to perform. So the counter-argument to the emphasis on speech understanding is that, well, yeah, that's what you want to do in the end, but if we want to look at the problem in isolation, we can actually make useful progress, because if we improve the accuracy of the words coming out, then you're going to improve the end-to-end performance of a speech understanding system. And the counter-argument on putting too much emphasis on tuning parameters is that you actually have to have really, really well-engineered baseline systems in order to do good research. If you're going to try out a new idea, you have to compare it against a very, very well-engineered system, or else you don't have any confidence that it's going to work across tasks. One of the big challenges in the area right now is that while there are some standardized tasks, there's also a lot of diversity in what people do, and it's very hard to believe sometimes that a technique that works in one lab in one setting is going to actually apply in different labs in different settings with different speech recognition systems. Anyways, getting back to Pierce's letter, he'd made these very valid criticisms of the field. Unfortunately, he was also really, really harsh. So the letter included comments like, a general phonetic typewriter is simply impossible unless the typewriter has the intelligence and a knowledge of language comparable to those of a native English speaker of English. And then on the topic of tuning parameters, speech recognition has a scarcity in the field of people who behave like scientists and of results that look like science. He actually compared the tuning of parameters to what a mad scientist would do rather than a real scientist. One of the end results of this was that it killed speech recognition research at Bell Labs for many years. It did have a positive impact, however, too, because this letter served as partial impetus for the beginning of a program funded by DARPA, the Defense Advanced Research Projects Agency. I have the D in parentheses because over the years sometimes you have the D, sometimes you don't, depending on the leanings of whatever administration is in power at the time. And they, in 1971, started a program focused on actually trying to do some sort of speech understanding. They wanted to achieve a breakthrough in performance in speech recognition by integrating speech knowledge, linguistics, and artificial intelligence. One of the key ideas that this program introduced was the notion of a competitive evaluation, where different people working on the problem would have a standardized set of training data that they could work with and a standardized task on which their performance was going to be measured. In this particular case, it was looking at connected speech with cooperative speakers, a 1,000-word vocabulary, which was large at the time, but as Sanjeev pointed out, is considered fairly small now. A fairly artificial, constrained syntax that the speakers had to adhere to in working with the system, and they wanted to go for something called less than 10% semantic error rate. And they also had to target performance that this would take maybe a few times longer than real time on a 100 MIPS computer. What that means is that if you have, say, a 1-minute clip of speech that you're trying to recognize, you could take 2, 3, 4 minutes to process it and get an answer out. So this did lead to an important turning point in the field because it led to the demise of sort of knowledge-based and rule-based systems in speech recognition. The DARPA evaluation tested 4 systems. 3 of them were very much based on notions of AI at the time, expert systems, rules, trying to encode expert knowledge within a system. And then there was one that was based on these ideas coming from information theory, communications based on probabilistic models. This was CMU's Harpy system. It integrated the knowledge sources in a reasonable way and trained parameters in a statistical data-driven manner. The end result was that Harpy won hands down, and none of the other systems came even close to meeting the program objectives. This led to a significant shift in the field and a general adoption of these data-driven methods. One person who summed this up pretty well was Fred Jelinek, who at the time was the director of speech recognition research at IBM and is now a professor here at Hopkins, who said something along the lines of, every time I fire a linguist, the speech recognition error rate improves. So let's talk about the probabilistic approach. You've seen this equation already, thanks to Sanjeev. We're going to cast the problem of recognizing speech as trying to find some sequence of words that is the most probable given the acoustic input and some set of model parameters. Apply Bayes' rule, throw out the probability of the data because, well, that's what you've got, and we end up with this so-called fundamental equation of speech recognition, where you're trying to find the sequence of words that maximizes the product of the observed acoustics given the word sequence and the observed word sequence. Now, why is this a useful framework? First of all, thinking about it in terms of probabilities gives us a way to integrate multiple sources of knowledge. We've already done this here by breaking it down into an acoustic model, which only has to worry about a sequence of acoustic features given some hypothesized word sequence, and then a language model, which all it really has to know about is how likely different sequences of words are. It also gives us a way to deal in a principled manner with uncertain inputs. Because as you heard in the audio examples that Sanjeev played, there's a significant amount of uncertainty if you're looking at just little segments of audio. You actually have to integrate knowledge over long periods of time to figure out what's being said, particularly in conversational speech. Okay, so the implementation. Again, Sanjeev covered some of this. The feature extraction in a speech recognition system corresponds to finding these acoustic vectors X. The acoustic model is assigning probabilities to acoustic feature sequences given some hypothesized sequence of words. The language model gives us a probability distribution over word sequences, and then the search implements this argmax operation. So let's talk about feature extraction. What are we trying to do? I think you've already heard some of this, so this is sort of a high-level overview. We really have four main goals in doing feature extraction for speech recognition. We want to characterize the aspects of the signal that are related to the linguistic information. That you absolutely want to preserve. You want to suppress as many aspects of the signal as possible that are not conveying linguistic information. So if you're a speech recognition system, you really don't care what the emotional state of the speaker is in most cases. Maybe if you're a customer service dialogue system, you do care, but that's probably handled by a separate module. We generally throw out pitch, except in the case where we're dealing with tone languages like Chinese or Vietnamese. And any other sort of information about acoustic background and stuff, we want to throw that away if we can. Doing that is actually not an easy task, however. We want a concise representation. So the models that we use can cope with series of acoustic features that are maybe up to 64 dimensions and are being updated 100 times a second. We don't have very many models that scale well to much larger feature dimensions, although that's an area of active research. Finally, we want to conform to the constraints of the acoustic model. So the standard acoustic model is going to be a mixture of Gaussians, and those Gaussians are going to have diagonal covariances. So you want a feature representation that's going to play well with the statistical models that you're using to give you your probabilities. So again, Sanjeev showed you some of this. The standard recipe for doing feature extraction is to extract some sort of a smooth spectral envelope from the signal, typically 100 times per second over a window of 20 or 25 milliseconds. That's typically implemented with a fast Fourier transform that gives you a linear representation of frequency. There's then a frequency warping operation that's applied so that you have high resolution at low frequencies and low resolution at high frequencies. This has traditionally been justified by parallels to what happens in the human auditory system, that we have higher resolution at low frequencies and low resolution at high frequencies. You can also justify it purely in information theoretic terms, because if you look at the distribution of information over frequency, information about what's being said, about the basic speech sounds, you're going to find that the lower frequencies are much more information-rich than the high frequencies. So this also justifies having more resolution in the low frequencies. We do some sort of a compression of this spectral envelope to limit its dynamic range. This just makes it easier to model with the Gaussians that we're working with. A log or some sort of power compression is typical. We do a decorrelation of the spectral representation. This is typically done with a discrete cosine transform. This gives you the Mel frequency Kepsler coefficients that you've probably heard about. And then finally, it's really important to include some sort of information about the local temporal evolution of the features. A standard approach is to use first and possibly second order temporal differences. Another approach that we've been advocating at IBM and found to be pretty useful is to simply concatenate some number of frames around the current frame and then do a linear projection. Okay, so a disclaimer. That's the standard recipe, but spectral envelopes are extremely fragile. You have changes in background noise, you have different channel characteristics, you have room reverberation. All of these things can drastically affect the spectral shape in some short instance of time. And you see this in the performance of speech recognition systems when you change the acoustic conditions. They break. And much of that tendency to break can be blamed on the representations that we're using. So there has been quite a bit of work done on looking at alternative representations for speech. And one good summary of this is something called Pushing the Envelope Aside, which is an article in IEEE Signal Processing magazine. And the view taken here was that you really want to look at the temporal evolution of the signal more than just the spectral shape. Another way to get a good perspective on this is to talk to Hina Kermansky while you're here, because he's been doing a lot of research in this area. Okay. So that's all I'm going to say about the feature extraction for now, unless anybody has any questions on that topic. Okay. Okay, so let's go on to acoustic modeling. So getting the probability of a sequence of acoustic vectors given some hypothesized word sequence. So as you heard from Sanjeev, most automatic speech recognition systems are going to use what's called a phonetic representation of the words. So we're going to break words like cat down into a sequence of phones. This is a specific notation for them. So cat becomes ka, a, ta. Dog becomes da, o, ga. The being a frequently used word and a short function word, often you see a couple pronunciations. So you see the and the, for example. So what do I mean when I say a phone is a basic unit of speech? What this means is two things. One, if you change one of these units, you can change the identity of the word. Two, these units are not readily broken down into smaller subunits. In some sense, they're atomic. The counterargument to that is an idea known as phonetic features, which will describe phones as a bundle of a number of different features, such as voicing, whether your vocal cords are vibrating or not, manner, place of articulation, where the constrictions in the vocal tract are. But again, that's more of an area of research. For our purposes, we're going to say, okay, phones are atomic units, and we're going to treat them that way. The other nice thing about a phonetic representation is that it lets you recognize words at test time that you never saw during training time. You just have to see enough examples of each individual phone, and then, as Sanjeev said, you can string them together to make words that you never saw before, which is nice. A couple disadvantages to the phonetic approach are that, well, one main disadvantage is that it can be difficult and expensive to get a good dictionary that covers a large number of words for a new language, particularly if that language has a complicated mapping from spelling to sound. A couple examples of this are English, which anybody here who's not a native speaker of English should know pretty well. There are many different sequences of letters in English that produce the same sound. It's very, very hard to learn because English is this strange hybrid of Anglo-Saxon, French, and just about every other language that we have borrowed words from. Another example is Arabic, where in standard written Arabic, you actually are leaving out a lot of information about short vowels and other variations of pronunciation. So it can be quite difficult to get a good phonetic dictionary. Nevertheless, most of the time that's what people use. You just have to invest time and money in getting one, and then you're good to go. Okay. So as Sanjeev showed you before, we typically will model phones with hidden Markov models. I've got a picture here. The idea is that let's break the terminology down a little bit. When we say hidden, what it means is that we assume there's some statistical process that's characterized by a set of discrete states, and we don't actually know at any given time what state is active in producing the features that we're seeing. It's a latent variable. So we don't know how to assign individual vectors to individual states. We have to infer it somehow. And then Markov is the other important word here. The idea here is that what we're seeing now, the present state, is going to be conditionally independent of the past given just the previous state in the hidden Markov model. So it's what's called a first-order Markov assumption. This is an important constraint because it lets us do very efficient forms of inference. It lets us do dynamic programming. We don't have to keep track of an exponentially large state space going back into the past, which we would if we were conditioning on more than a single state. Now, in reality, this Markov assumption is just that. It's an assumption. It's an approximation. Speech is produced by a physical system which evolves slowly in time. So there's actually a high degree of correlation across time. So the conditional independence assumption is not necessarily correct, but it seems to be good enough for our purposes. Also, if it were true, then language models wouldn't be so useful because that's giving you much longer range information. So it's an approximation, but it's good enough for the acoustic modeling. Okay. And as Sanjeev pointed out, a very standard setup for these hidden Markov models is to use a begin state, a middle state, and an end state to describe the phone. Okay. So there's three key operations that Sanjeev discussed also, and I believe you heard about previously from, what, Jason Eisner? Okay, yeah. So there's the forward-backward algorithm, which gives you a distribution over the hidden states at each time t, given some word sequence and a set of acoustic observations. There's what we call the constrained Viterbi algorithm, which is given a word sequence, you want to find the best assignment of states to points in time, given your word sequence and your observation sequence, and then the Viterbi algorithm, which gives you your best state sequence given an acoustic observation sequence. The first two are useful for training hidden Markov models, and then the third one is what we typically use when we're trying to do speech recognition. Okay. Now, one of the tricks in doing a good speech recognition system is that just a pure phonetic representation is not good enough. So Sanjeev alluded to this. There's a lot of variability in the acoustic realizations of phones depending on what's being said. So one exercise is you put your hand in front of your mouth and you say spin, and then you say pin. And if you do this, you're going to feel some differences. So the P in the pin is going to be typically preceded by a puff of air. May depend a little bit on what your native language is. The P in spin is not going to be preceded by the same burst of air. It's going to be what's called unaspirated. So these sort of variations are called allophones by linguists. More generically, you see effects such as nasalization, where a preceding or following nasal and n or ng is going to change the realization of a vowel. You see this all over the place. So we have to deal with this in some way. And we want to deal with it in a way that's data-driven. So the standard technique in speech recognition is to use decision trees. So the recipe for doing this is, okay, assuming that we have some set of models already, we can take our training data we can do this forced alignment procedure. So now for every utterance in the training set, we have an assignment of acoustic feature vectors to states. Then, for each state in these phone models, collect all of the observations assigned to that state by the forced alignment process, and then you treat that as a pool which you start splitting based on likelihood to grow a decision tree. So what you're going to do is you're going to take a collection of acoustic vectors and you're going to ask a set of questions about the phones adjacent to the current phone. And then you're going to take the question that gives you the best improvement in likelihood from splitting your data, and you're going to take that and then you're going to do this recursively. And then at the end, you're going to prune the tree, all of the trees at once using log likelihood to come up with some set of context-dependent states. I'm going to illustrate that in more detail in the next couple slides. So here's a sample decision tree that I actually took from one of our speech recognition systems for, I think it was English Broadcast News, for the first state in an ah phone. So the first question asked is the preceding phone, so the notation here is the integer on the left indexes adjacent phones. So -1 means the phone immediately preceding the current one. Is it a sonorant? Yes or no? If no, is the phone 2 positions preceding silence? Yes or no, and so on. And these questions are basically assignments of the phones into different groups based mostly on phonetic features of the phones. So things like nasals, and labial, which refers to having a constriction of the lips, so buh, and so on. So this gives you a way to come up with a set of models that more accurately describe what's going on in the speech signal. So rather than trying to handle all of the variability of the phones at once, you're going to divide it up into a set of models that can be sharper and more precise. Is this clear? Okay. Okay, so moving along, once you've done this process, I should actually add a couple other points. These decision trees can ask other questions. So what I'm showing here is just asking questions about phonetic context. It's also quite common to have some notion of position within the word. So if you're close to a word, the beginning of a word or the end of the word, you might actually want to have different models. You could also do the same for syllables if you're so inclined. That's actually quite a common technique. You will also see cases where if you imagine that you're going to deal with speakers who have many different accents or dialects, you might actually ask questions in these decision trees about what the accent or dialect of a given speaker is. You then have to have some way of estimating that online. This is a less common approach, but it's one that has been explored and is one possible route to handling some of the effects that Sanjeev was illustrating, where you see different dialects having radically different realizations of vowels in common words. Okay. So moving on to how we model the acoustics. The standard model here is once you have one of these context-dependent states, you're going to model the acoustic feature vectors with a mixture of Gaussian distributions. This is the equation here. You've got a sum over some number of components. Each of them has a weight, and then the rest of these are just parameters for a multivariate Gaussian distribution. Typically, we're going to constrain the covariance matrices to be diagonal. This is mostly for reasons of computational efficiency and also dealing with the fact that you just need to have a lot more data to estimate a full covariance matrix. Why do we use Gaussian mixture models? There's a few reasons. It's mathematically tractable. It's quite easy to do inference with them. It's quite easy to do estimation with them. And because you do have a mixture of components, it's actually, you can approximate to almost arbitrary accuracy any number of actual data distributions that you see. Okay. So the Gaussian mixture models are going to be trained using the EM algorithm that you've already heard about. Given some initial estimates of the Gaussian mixture model parameters, you can define what we call a posterior probability of a given vector corresponding to a given component in the mixture. This is what we call the expectation step. And then we can do parameter updates of the models. So the means just become a weighted average of the observations. Covariances are a little bit more complicated. But again, we're just weighting things by these posterior probabilities, this P of j given x and q. And the normalization is just the sum of these posteriors over all of your training data. And you just iterate this process to convergence. Now, there are several practical issues here. The first thing is that how you initialize this process matters a lot. The reason is that EM is only a local optimization procedure. You start with some set of parameters, and then you're taking local steps in your parameter space to improve your likelihood. You're not doing any sort of global search over all of the possible parameter space, all of the parameter space to get the global optimum. You're just doing a local search. So the better your starting point, the better your final models are going to be. So there's a couple ways that we can do initialization. If we have some alignment of the data, we can just randomly assign samples to some number of components and run EM a lot. Or another very common recipe is mixture splitting. So first you start with just a single multivariate Gaussian per state. You train those up, then you split those Gaussians into 2 and then into 4 and so on, and sort of gradually grow your models over time. In practice, both of these approaches seem to work reasonably well. I personally have a preference for the first one because it takes fewer passes over the data and seems to work fine. Another important issue that's a practical issue is regularization. We're maximizing likelihood. If you have a component that gets only a single data point, you're going to shrink your variance to 0. You're going to get an infinite likelihood. Your model's going to be very happy, but it's actually not going to be very useful in practice. So you have to sort of prevent that from happening. There's a few ways of doing this. You can apply some sort of a floor in the variances. You can discard mixture components that don't get a lot of data assigned to them. Usually you want to do both. And exactly what the floor is going to depend on your front-end feature extraction. And what not a lot of data means is also going to depend on the task, how much training data you have, and so on. Finally, there's a question of model selection. So how many mixture components do you want to assign to each state? Again, there's a set of different approaches to doing this. One very standard recipe is to say, okay, well, we're going to treat silence specially because there's a lot of that. There's a lot of variability. We might give it a lot of components, and then every other state's going to get some fixed number of components. It's nice. It's easy. A slightly better approach is to say, okay, I'm going to look at how much data I have assigned to each state in my training set, and then I'm going to base the number of components on counts. So one approach that we've found works pretty well at IBM, it's actually a method that originated at Cambridge, courtesy of Dan Povey, was to say, okay, I'm going to take the number of acoustic vectors that align to a given state. I'm going to take the raise that to the 2/10 power and make the number of components that I assign to a state proportional to that. And then I'm going to basically make the constant of proportionality a tuning parameter that the system designer can set. So do you want 100,000 Gaussians, 200, 50,000, whatever. Finally, there are a number of Bayesian methods based on things like the Bayesian information criterion or variational approximations or such that can also give you a way of deciding on the number of components per state. My perspective, honestly, Bayesian methods are great for publishing papers, but they're going to have a hard time competing with a well-engineered, more empirical approach. It's my bias. Okay, so putting it all together to train hidden Markov models then, Given some set of initial model parameters, we're going to either use the forward-backward or Viterbi algorithm to get an assignment of each feature vector in a training corpus to an HMM state, or a set of states if we're using forward-backward. Then it's a soft assignment. You could have multiple states active at any given time. And then given this assignment, you run EM for each Gaussian mixture model set to update your GMM parameters. A hidden Markov model does have transition parameters. In practice, at least in large vocabulary recognition, we don't use them because they don't really seem to have much effect on the performance of the final system. The language model matters a lot more, so we just don't bother. And then, yeah, you iterate this process to convergence. Okay, so note that I said here, given initial model parameters. Where do these come from? It's an iterative process. But how do you start the process? There's two ways to do this. If you're lucky, you've already got some speech recognition system that is close enough to the task that you're trying to build your new system for, that you can use it in this forced alignment process to come up with an initial assignment of your acoustic feature vectors to states, and then you can just bootstrap the process from there. Either typically using, say, a random assignment and EM to get your initial Gaussian mixture models. If you're not lucky, if this is a completely new task and all you have is a collection of acoustics for your utterances and a collection of hand transcripts of those acoustics and a dictionary, what are you going to do? Then the standard recipe is something called flat start training. So we're going to say, okay, we have a dictionary. We have transcripts for each utterance. So we'll take an utterance. We know the sequence of words. We can turn that into a sequence of phones given our dictionary. And then we're just going to say, okay, we have n phones. We're going to take the acoustic, chop it into n equal length pieces, initialize our Gaussian mixture models based on that completely bogus alignment of the data. We're going to use really, really simple models, just a single Gaussian per state. We're not going to do any conditioning on the context, and then we're going to run a whole bunch of iterations of forward-backward training. This process works pretty well in practice, despite there being a couple of complications. So you've got a dictionary, but what if you have more than one pronunciation per word? What do? Well, the answer is you pick one at random. If you want to be careful, maybe you take each utterance and you sample from your dictionary 10 different times to get 10 different possible sets of pronunciations, and you accumulate the statistics for all of those just to get a smoother initial estimate. The other problem is, what do you do if you have utterances where there's a silence, a long silence in the middle? Then you know that, but in your initial flat start, you're not going to be able to hypothesize silences anywhere. All you have is a sequence of words. You have no models to tell you where the silences are. So what do you do there? The answer is, well, you close your eyes, you run a few iterations of forward-backward training until your likelihood has gotten pretty good. Then you allow your models to insert silences where they seem to be likely and continue the process. So this is another illustration of sort of a common theme in speech recognition, which is that we almost always use some form of iterative training. We start with very simple models. We train those up, and then we make those models more complex and grow them over time. And again, it's just because EM is a local search, a local optimization, so you want to always start from a good initialization. Okay. Any questions on this? I should add there is one other way to get initial model parameters, which is there are a few data sets out there that have been hand transcribed at the phone level. The most well-known one is the TIMIT database, and you could actually initialize your models from based on the labor of a lot of linguistics graduate students, but that's not the common case. Okay, language modeling. Should also do a quick time check. Okay, in good shape. So we want to get a model that gives us a distribution of probability distribution over word sequences. Why do we need one of these in the first place? Well, the mathematician's answer is use Bayes' rule. You need to have a prior distribution in order to do the search at all. That's certainly true. An engineer's answer is that it actually simplifies the search procedure quite a bit because you can use the language model to penalize unlikely word sequences and throw them out earlier and spend less time doing the search process. The user's answer actually goes back to an old IBM VIA voice ad, which is that it lets you disambiguate between homonyms. So write a letter to Mrs. Wright right now. Write, and right are all the same sounds, but the spelling's entirely different. A language model can actually help you sort this out. So Sanjeev showed you this. A precise computation of the probability of a sequence of words would say, okay, we're going to take the probability of the first word given some start symbol. We're going to multiply that by the probability of the second word times condition on the fact that we saw the start symbol in the previous word. And we're just going to do this recursively until, and finally we're multiplying by the probability of some stop symbol given the entire preceding sequence of words. Now this isn't practical because the chance of observing a sequence of m words decreases exponentially as you increase m. So you have a massive data sparsity problem here if you go for very long sequences at all. So the standard approximation is this n-gram approximation, which is to say, okay, at a certain point we're going to just ignore the words farther back in the history. So we're going to approximate this product here by a product of probabilities conditioned on fixed length histories. So we're going to say the probability of word 1 based on, well, we're going to replicate the start sequence, the start symbol, and we're just going to do this. So at the end, instead of conditioning on all previous words, we're just going to condition on a couple of them. You have much more chance of seeing these, what are called trigrams, collections of 3 words, in a training corpus than you are of, some arbitrary long sequence of words. So how do we go about doing this in practice? We're going to collect as much text data as we can get our hands on. State-of-the-art systems will use billions of words of text if the researchers have access to it. And then we're going to go through and we're going to count word co-occurrences up to the maximum desired order of the history. So it's a long, fairly memory-intensive process. You need good computer programmers to implement this so that you can run this in a reasonable amount of time. And you want to buy machines with lots and lots of RAM. Then we need to smooth. We can get maximum likelihood estimates just by normalizing the counts. We have to smooth these because even though we're doing an n-gram approximation of some fixed order, there are going to be sequences of words that we would like to be able to recognize that we did not see in our text corpus, no matter how much text we collected. And if we let our language model assign a probability of 0 to one of these desired word sequences, it will never output it. We're in trouble. So we have to move some of the probability mass from what we did see to what we didn't. And smoothing language models is a whole big area of research. Finally, in practice, we'll often get better results by training separate models on different data sources. So consider the problem of doing language modeling for broadcast news. You will build one language model on the acoustic transcripts where somebody sat down and actually wrote down every word that the reporters and anchors and so on said. And then you might go and collect a whole bunch of newswire data. So this is mostly from print sources. It's not going to be exactly the same as spoken language, but it's going to be close enough that you could train up a language model on that and then interpolate it with the language model trained up on the spoken language, and you're going to get better estimates overall and better end-to-end performance in your speech recognition system. Okay, so I lied to you earlier when I put the fundamental equation of speech recognition up. So did Sanjeev. We don't actually optimize just the probability, we put in something called a language model scaling factor. We boost the probabilities coming out of the language model by some factor between 5 and 25, and we set that boosting on development data. Why? Well, I've never heard an explanation that's completely convincing. There's a couple reasons that people have cited. For example, the acoustic models are overconfident. The acoustic models making conditional independence assumptions not actually respected, and we have to compensate for that. But the real answer is the engineer's answer. It works better in practice. It also highlights an important issue in speech recognition, which is that, yes, we are combining evidence from different kinds of from different information sources. We're combining some model of acoustics with some model of words. But actually doing that right is hard. So we have to introduce tricks like this. It is what it is. Okay, going on to the search. So typically we're going to use the Viterbi algorithm. We're going to approximate a search for the best word sequence with a search for the best state sequence, as Sanjeev's talked about. And we can think of this as performing a dynamic programming search on a large graph. Arcs in the graph are going to correspond to states in your hidden Markov model, and are going to have costs which are proportional to negative log likelihoods coming from the acoustic and language models. And then at each step in the search, the dynamic programming entries are going to be updated with your lowest cost path that can reach the state, a given state at a given time. What does the search space look like? So here's a very simple example. We're going to take a language model that only permits two sentences, the dog and good dog. We can represent it with a finite state machine that looks something like this. This is a graphical representation of such a thing. You have a start state. You transition from the start state to the first one, and you emit this start symbol. Then you can transition from here to here, emitting the, here to here, emitting dog, and then to a final state, emitting your stop state. Or you can take the alternate path and emit good dog. Okay. Thing is, sometimes people put silences in. So if we want to hypothesize all possible silences between words, then the search space starts to look like this. Then, okay, we've got different pronunciations. So the could be said the, or it could be said the. So we have to do this sort of expansion to every arc in this. Then we have to add context dependence. So the dog, because the D here could depend on the previous and following identities of the previous and following phones, then this graph can grow even further. You can have sort of basically a big blow up of the size of the search space. End result, for a large vocabulary task, I looked at one of our search graphs, and we had 45 million nodes and 190 million arcs in it. This comes from starting with actually a fairly small language model, and then taking the language model, expanding out all possible pronunciations of words in the language model, adding in the context dependence, and then doing these finite state operations, graph determinization and minimization, to try to get a compact representation of the search space. Even so, it's really big. And like I said, that's actually with a small language model. So dynamic programming has this nice property that it's number of states times the number of time steps, more or less. But that's an awful lot of states and an awful lot of arcs. So to do this in a reasonable amount of time, we have to prune the search. We have to only consider paths that are likely to lead to the final best path. We're going to throw away a lot of unlikely state sequences as early as possible as we can in the search process. There's a couple ways to do this. One is what's called rank pruning. So at any given time step, you're only going to keep, say, the 10 or 15,000 most probable hypotheses. You can also do what's called beam search, which is you're going to look at the best scoring path at any point in the search, and you're only going to retain competing paths that are within some likelihood, called the beam, of that best path. A modern large vocabulary search process is going to use both of these. Now, there's two different ways of doing this search. The first is what's called static search. So we're going to use finite state operations to compile all of our information sources, our language model, our pronunciation dictionary, the decision trees that give us a set of context-dependent states, and so on, into a single large graph. We're going to use determinization and minimization to make that graph as compact as possible. And then we're going to do speech recognition by doing Viterbi search on that graph. This has a couple advantages. You can make a static decoder very, very fast. The search space is completely pre-specified. All you have to do is run your acoustic model, run the dynamic programming, do your pruning. It can be written very efficiently in a surprisingly small number of lines of code. Catch is that because of the nature of the finite state optimizations, you have to constrain the size of the language model that you use. You can't use, so language models can be very, very big. They can have lots and lots of parameters. You could have hundreds of thousands of n-grams represented within the language model, but you can't compile a really big language model into one of these static search graphs. You're going to run out of memory at some step in doing the finite state optimizations. So if you're going to go with static search, you're going to often use some sort of multipass approach where you use the static search to produce a collection of likely hypotheses, either what's called an n-best list, where you get, say, the top 10, top 100, top 1,000 most likely word sequences, or a lattice, which is a graph structure that gives you where the arcs are words and the nodes correspond to points in time, that will encode a very large but still much smaller than the original search space. And then you'll go back afterwards and use some better language model to come up with a rescored hypothesis. You go through and say, okay, we'll throw out the old language model scores, we'll use our better language model, and that will give us our final hypothesis. The other approach is what's called dynamic search. So you're going to construct the relevant portion of the search space on the fly. Remember, we're doing pruning. We're not considering all hypotheses. We're just considering the most likely ones. So we can sort of incrementally expand the search space on the fly and only worry about searching in that portion of the space. The advantage is that you can use a full language model in your search from the beginning, but typically there's a lot more computation, so it's going to be slower, and it's also a much more complicated piece of software to write. Okay, so where do we stand right now in speech recognition? And before that, though, any questions on search? Okay. So you've probably already seen this. Our standard measure of speech recognition performance is word error rate. We're going to take some reference, like the dog ate my homework, take the system output, and we're going to do an alignment between the hypothesized and reference word strings in a way that minimizes the number of errors. Once we've done that, that's just another that's just another form of dynamic programming to do that. Once we've done that, we're then going to count up the number of errors, divide by the total number of words in the reference, and that gives us what's called a word error rate. So given that we've, for every word, how many times are we going to get it wrong? And we're going to count substitutions where the recognizer outputs one word but the reference has another, insertions where you hallucinate words, and deletions where you throw them out. Note that this can actually be bigger than 100% if you're really not doing well. Okay, so what happens if we compare the performance of state-of-the-art systems to humans? And remember, Sanjeev talked about how different tasks have different levels of difficulty. So something like connected digits, where it's spoken quite clearly in a very quiet studio-like environment, people's error rate is minuscule. Best machine performance is still like 0.7% error rate. Wall Street Journal, which is somebody getting up in front of a microphone and reading stories out of the Wall Street Journal, Humans are about 1% word error rate. Machines, roughly 7.2. Depends on which person's results you look at, but it's a good ballpark figure. As for clean acoustics, say 10 dB signal-to-noise ratio. We're going to add some noise to this red speech. People don't budge. Goes up just a little bit. Machines break. Word error rate gets a lot worse. And then you heard the telephone conversations. If you actually have people sit down and try to transcribe every word in a telephone conversation, they're well trained. The word error rate's maybe 4%. 15% is a very good performance on telephone conversations. And Sanjeev said it can actually go much higher. It's going to depend a lot on who's talking to whom, how much training data you had. Is the person on a cell phone, a speaker phone, or is it just a handset? The 15% is from a very well-controlled data set. So what's going on here? Why are people so much better? Yeah?
Question for conversation. Is this annotated agreement is per person, or how do you get the gold transcriptions?
Good question. So this would be for an individual person transcribing compared to a gold transcription where multiple people transcribed it and then there was an adjudication process to get a final reference. But if you listen to this stuff for very long, you realize that doing any sort of word-level transcription of a telephone conversation, particularly between people who know each other and are familiar with each other, is very hard. The amount of reduction, the amount of variability in prosody and stuff just makes it extremely hard to do. So it's a ballpark figure, but it gives you a sense of the problem. Machines are much better, much worse than people. Yeah.
So I had a couple things
Mm-hmm.
been involved in this for many years. So on the connected digits, that's always an interesting point to me because I do believe machines have exceeded human performance. For example, if you dictate a credit card number over the telephone, more than likely you're going to have to repeat it 2 or 3 times to a person at the other end trying to transcribe it.
Mm-hmm.
Machines will very often to make it actually get it right or get very close to right.
One issue there is that the machine can do the checksum that the person can't.
There's that issue. And people attention level basically is a big issue, right? And I think that when we do these human benchmarks, we often don't really quantify that well. But attention level is a big issue in transcription tasks.
Absolutely, yes.
On the switchboard stuff, as you know, we spent too many years transcribing switchboard. And one of the things there that people don't often take into account is the transcriber's familiarity with vocabulary. So when we were using undergraduates to transcribe even something like switchboard, there were a lot of the financial conversations that the students didn't really have the vocabulary in the background to understand what the terms were.
Mm-hmm.
And the error rates were actually pretty high initially.
Yeah, I've had the same experience dealing with call center data internally at IBM. It actually got to where I could guess pretty reliably which conversations have been done by the same transcriber because they made the same errors over and over and over again. So yeah, that's definitely, there are issues of human knowledge, attention level, just the problem of boredom that should be considered in these. These are sort of maybe, the numbers here are arguably maybe best case scenarios for humans. Definitely on the connected digits. I think this is actually from a study where it was a committee that was producing the human transcript. So it was really an adjudicated process. So this may be a little bit of an underestimate.
I think that's the TI digits.
Yeah. Yeah.
There's a long history to that, but machines actually can exceed performance on that. Can exceed that level of performance.
Mm-hmm. I guess, especially, as you say, in the wild. Okay. So yeah, what? Mm-hmm. I'm sorry?
What kind of errors do humans make on voice command? That 1%?
I actually don't know. You might miss, depending on the noise, you might miss some plural versus, you might make plural versus singular errors, although there's enough other evidence in the sentence that you're not likely to do that. I'm not sure, actually. I never saw.
I've never done this in Wall Street Journal, but I've tried to transcribe some switchboard, in fact.
Mm-hmm.
I could hear it, but I had to guess what it was because all I could write down is spelling based on what I heard it. I
Yeah.
had no idea what it was. And later on I found out it was the name of a company in the Dallas area. And one of the colors was Dallas. And then they bring the company.
That wasn't LTV, was it?
No, it was a...
Because we encountered that same problem with
Right.
transcription with the undergraduates.
Right. So I'm wondering whether the 1% is that kind, where you just don't know what it is, but you can describe the word.
Yeah, but I mean, the big take-home lesson there is just that the delta here
Yeah, that's
is so small.
Nothing changes with it.
Doesn't budge. So yeah, why are people doing so much better? What are they better at? It may sound like a glib answer, but the honest answer is really people are better at everything. The acoustic processing that's going on in the brain is much more sophisticated than anything that we're doing in a speech recognition system. The acoustic models are better. If you do tests like trying to do nonsense consonant, vowel, consonant syllables in isolation, and Dudley did a whole bunch of this at Bell Labs, I think in the 30s and 40s, trying to, or maybe even earlier, trying to help develop the parameters of the telephone system. If you compare what people can do on that to what a machine can do, it's a lot worse. And that's a purely acoustic task. Then if you look at the kinds of errors that machines will make on something like broadcast news, where the error rates are pretty low, a lot of these errors are going to be plural versus singular errors that a person, especially a native speaker, would never make because they have a very good language model and they can use other information in the stream of words to say, yeah, this has to be a plural, yeah, this has to be a singular. That's not captured by the Ngram language model. So people have better language models, and they do a much better job of integrating the information from the acoustics and the language model. They do a much better job of judging the relative reliability of the different information sources they have and putting them all together to just get a better overall guess at what's actually being said. Okay. So what are the strengths of the approach here, of the statistical approach? Despite things like the language model scaling factor, statistical framework does provide a solid mathematical foundation for algorithmic development. It's really nice to be able to write out equations, figure out reasonable update rules, figure out good algorithms. It gives us a very nice tool set for tackling the problem. Using the statistical approach also lets us compensate for what is a very limited understanding that we have of how human speech recognition works. As I quoted Fred Jelinek earlier, every time I fire a linguist, my error rate improves. Well, what are we doing instead? We're taking extremely simple generic models with relatively few constraints. We're using tremendous amounts of training data and lots of computation, and that lets us get something that works in a practical setting some of the time. Another nice summary of this is something that Hina Kermansky told me, or said when I was a grad student at Berkeley, that no knowledge is better than wrong knowledge. You should construct your systems in a way that you let the data tell you what to do. If you want to bring in some sort of prior knowledge, you want to encode that in the form of a regularization or a prior on your model. You don't want to necessarily dictate exactly what's going to happen, because the data may tell you something different from what you believed in the first place. What are the weaknesses? I've alluded to one, so has Sanjeev. Variability is the Achilles heel of automatic speech recognition systems. What you're going to get when you actually deploy a system is going to be different, possibly quite different, from what you had in your training data. And statistical models right now tend to work best when they get data that's exactly like what they were trained on. If there's a lot of variability, if the acoustics are different, if you have a different accent, a different dialect, words you've never seen before, things go wrong. The other issue is just one of expense. Developing a state-of-the-art speech recognition system for a new language or a new task requires a lot of effort. You have to collect a whole bunch of data, pay people to do verbatim transcriptions. And then you have to have a fairly highly skilled set of people sit down and just bang away at it, trying to build the best models that they can on that data set to get good performance. It's an expensive process. So what do we do to tackle this? On the variability, I think we do somehow have to bring in more knowledge. But again, we have to do it the right way. We have to use it as some sort of a prior or as regularization. We have to be able to do a better job of estimating the relative reliability of an acoustic model or multiple acoustic models and a language model given the current state in which the system finds itself, and then intelligently combine the evidence from these different information streams to come up with a better hypothesis. And as for the issue of expense, there's a lot of interest in using lightly supervised or unsupervised techniques where you don't have to have transcriptions to somehow bootstrap your models so that you can do the actual tuning of the system on a much smaller body of transcribed data. It's a research direction. It's not a problem that's solved yet, but it's definitely something that we have to do, particularly in order to deal with the large number of languages that are out there in the world. For more information, I think these slides will be available afterwards. There's a link here to a full set of lecture notes from a course taught at Columbia by Stan Chen and some of my other colleagues from IBM. And I want to thank Stan Chen because I went through his presentations and plagiarized a lot of the material to put this talk together. That pretty much concludes things. I can take questions. Sure.
So if you take the computational power or requirements for a state-of-the-art large vocabulary recognizer that can handle hundreds of thousands of words, how far off do you think that is from the computational capacity of the brain?
I have no clue. Every time I look at neuroscience, and I minored in it at Berkeley, I get the sense that there's just a lot more going on in the neurons than the very simple neural net models, for example, that we play with. You have people doing information theoretic experiments on things like insects. And a lot of this is on things like the avoidance response of the cockroach, why it runs away before you step on it. It has these sensors, these hairs sticking out of the side of its body that detect puffs of air coming towards it. And people have actually sat down and measured the information content in a single spike going down an axon from one of these cells that senses the movement of that hair. And it exceeds 1 bit. Because it's not just whether the action potential happened or not, it's the timing of it compared to other spikes in parallel axons and in the same one. So there's a huge amount of information processing in the brain, and I don't think we have any good characterization of it. My guess is that the human brain probably exceeds what one of our computers can do right now by several orders of magnitude. But yeah, I think so. I think so. It's when you look in detail at the neuroscience and just the complexity of what these neurons can do, it's huge.
So a related question is, when you talk about the performance and noise, this is one of the big areas where machines differ from humans, especially when machines have not been exposed to the prior exposure to the noise.
Mm-hmm.
And we talk about binaural hearing and all the wonderful things humans do, but if you strip all that down and you actually set up a very focused experiment where they're listening monoraurally and such, they still do much, much better than machines.
Mm-hmm.
What do you think is the big difference between the two?
I think a lot of it is you've got a much richer representation of the acoustics, and you've got a processing system behind it that can cope with that. There's been a lot of interesting work done on different front-end representations, various forms of physiological modeling that tries to come up with very high-dimensional representations of the acoustics. And the problem is we don't have the models that we can hook up to that in any sensible way. So my best guess is that you've got much more sophisticated acoustic processing going on, and you have processes that can do a very good job of figuring out which bits of the representation are reliable, which ones you can base decisions on, and which things have to be ignored or downplayed in making an estimation of what's being said. So there's much more sophisticated representation, and there's much more sophisticated integration of evidence across that representation to decide what's going on. We don't just have this very simple mechanistic, you're summing up log likelihoods from frame to frame over time. You're doing something much more detailed. Mm-hmm. Yes, both. Although to some extent, the order of the language model doesn't matter so much as just the number of n-grams. So just to give you a ballpark figure, so like our systems at IBM, we typically have to take a language model and prune it down to 5 or 6 million n-grams. Typically go up to 4-gram order and then we can compile a static decoding graph. But for, say, Arabic broadcast news, we may have hundreds of thousands of n-grams. We have, I think our current vocabulary is around 800,000 words. And there's just no way to put that through the FSM operations. So at that point, we have to do some form of dynamic decoding. That said, the dynamic decoder that we use does have embedded in it a lot of these finite state operations. So the first thing that you do is you build up just a simple word loop with that gives you the bigram language model. You can compile that, and that's going to be a relatively small number of n-grams. You can compile that into a fixed graph, and then the dynamic decoder actually operates on top of that. So a lot of the heavy lifting of expanding the search space is done offline with FSM operations, and then internally, mostly you just have to keep track of different states in the language model. Maximum order, I think we've played with up to 6-gram, particularly in a rescoring framework. I think some of the work on neural net language models might go to even higher order, but that comes at a cost of drastically reducing the size of your vocabulary. On the other hand, that lets you handle the most common word sequences, which is what's going to have the most bang for the buck on the word error rate. Yeah.
Has there been any success using, I know you said prior language, but has there been success using syntactical models in addition to the bigram, the n-gram models?
As a matter of fact, yes. There's been a lot of use, particularly, again, in a rescoring framework where you can constrain the search space that the syntactic language models have to deal with to a list of 100 or 1,000 or 10,000 word sequences. The work that I'm most familiar with is the work at IBM, where we're using syntactic features within a neural network language model to do rescoring, and we're getting some improvements fairly consistently across tasks, mostly in the context of doing transcription of news broadcasts in Arabic and sometimes Chinese. So it's been a relatively small gain over just doing a really good n-gram. But it's there, and it's an active area of research. Mm-hmm.
So you mentioned most folks use this type of approach. Are there any kind of left field or totally different views of this that you see comments in the future? So we're just going to keep a little bit of this model, or is there going to be some breakthrough with some other view of
I honestly don't know. There's been some interesting work in the machine learning field on this idea of what's called deep belief networks, where you are representing, where you're doing sequence recognition using some fairly large set of binary latent variables that don't have a pre-assigned semantics but are learned from data. There's been a lot of success in applying these things to motion capture and a number of other forms of temporal signal processing. And it's interesting to think about applying them to speech, but you also have to say, well, these are often dealing with somewhat shorter sequences than we have to deal with. So that's one area that I think is interesting. But you never know. It's one thing that has hit me over the 11 years I've been at IBM is that this model has held up pretty well, and you always have to compare some new idea to a carefully engineered state-of-the-art system before you can believe that it's going to go anywhere.
What's the state-of-art results as to translation of foreign languages such as Chinese and Japanese, something like that?
It depends very much on the task that you're working on. So if you have a constrained task, and it depends on the language pair. This isn't an area that I work in personally, but I work with people who do it. So Arabic to English is not too bad, particularly if you have a constrained task. So there's a DARPA-funded program called TransStack, which is aimed at doing things like enabling U.S. soldiers who don't necessarily speak languages like Arabic or Pashto to interact with people who don't speak English in a fairly constrained environment where they're trying to do things like, asking people, are you armed? Or a medical application, what's injured? Let's try to diagnose a problem here and get you patched up. That works pretty well. If you consider something like taking Chinese news broadcasts and translating to English, the results are much more mixed. You will occasionally have, so we have demonstration systems that do this. And if you watch, it'll actually give you English closed captions to a Chinese news broadcast. And you'll go along, and most of the time you're able to kind of get some gist about what they're talking about. And then every so often it just breaks down, and you have what we call word salad. It's just a sequence of stuff that you can't make heads or tails of. And part of it's that Chinese and English just have extremely different structures in the language. There's a lot of information that's implicit in Chinese that's explicit in English, and getting from one to the other is not something that we do very well. So it's still a very challenging problem. And if you try to do speech-to-speech, it gets even harder. But I'm afraid I can't put good numbers on it because that's not the area I work in. Mm-hmm.
So to follow up on the question of alternative techniques, you're saying that you need to compare them to sort of state-of-the-art to know whether they're going to be any good. Does it make more sense perhaps to compare them to older versions of the HMM approach to know if they have promise rather than to know if they're being the best?
It's a fair question. No new technique is going to do as well as a carefully engineered state-of-the-art system. It's just a fact because I think the point you're making is there's many, many years of engineering and effort that's gone into optimizing what the standard recipe. And some new idea is going to be maybe the work of one or a handful of people working over some period of time. So you always have to take that into account. It's really a judgment call at some point. But you at least have to be aware of where the state-of-the-art is compared to whatever technique it is that you're exploring. And you have to have some vision of what's causing any gap in performance between the two techniques and how that gap can be closed over time. But yeah, it's a necessary comparison, but it's not a fair comparison. Other questions? Mm-hmm.
You mentioned that Bayesian approach is not so practical.
Mm-hmm. Okay, so the main issue is that many of the Bayesian methods require just significantly more computation for things like model selection or for trying to marginalize over different hidden variables. And in a very large vocabulary system, the amount of computation that costs can be really, really significant to the point of making the technique impractical. And by the time you've made enough approximations to make the technique practical, then there may be some more ad hoc empirical method like flooring variances or throwing out mixture components that have not a lot of data assigned to them that is going to work as well and isn't going to require the amount of computation. So it's again, it's an engineer's perspective of what works in practice. It's not entirely fair because the empirical methods have had significant amount of tuning applied to them to get to where they are. So you could imagine a scenario where you have a new task and maybe you could run a Bayesian method once, get an answer, and just go on, whereas the person using the empirical methods would be trying several different configurations before proceeding. But yeah, it's mostly just a question of computational effort. The simpler the technique is, the more likely it is to be successful simply because you're not going to have to make as many approximations. Mm-hmm.
Curious if you've worked on enrolled user systems, how you balance the two different sources of training data, the sort of general information about speakers of the language and information about your target speaker?
It depends a lot on you often base it on how much enrollment data you have. So if it's a small amount, you'll typically do various forms of what's called adaptation. So you're going to tweak your model parameters slightly in a very constrained manner. One of the common ones is called maximum likelihood linear regression. So you apply a linear transform to the means of your Gaussians that is going to maximize the likelihood given some enrollment data. If you have a lot of it, then you're actually going to imagine doing some update of all of the model in a much less constrained manner. There it actually looks like a form of training where you come up with counts on your enrollment data and then you go back and you update your model based on that. But yeah, I'm not too familiar with this, how you choose sort of the step size to do that adjustment. It's not an area that I've worked on. But I think it's one of those things where people who work on it will come up with some fudge factors that they've used on a lot of tasks and say, okay, we'll add these in, but we're going to weight the training data by a factor of 10 higher or 100 higher or whatever.